This will be a video with a few different examples of simple logarithmic evaluations. And this is going to be using our definition of a logarithm here. And so if I have log, here we go, log base a of x equals y is the same as a to the y equals x. And I can use that definition to determine or to evaluate what the value of y here is. How can I do that? It's a little bit different. It's a little bit different of an analysis. But what I really have is if this is log base a of x equals y, then my a is 2 and my x is 16, right? And so what I'll really have here is 2 to the y equals 16. And so it's going to be 2 to the what equals 16. Well, 16, if I think about, back to my old, what is a number, right? And go back to my factor tree. The last number is divisible by 2, so the whole thing's divisible by 2. So I got 8 and 2, and then 8 is 4 and 2, and then 4 is 2 and 2. So what I really have is 2 times 2 times 2 times 2 is 16. That really means that 16 is 2 to the fourth, right? Because an exponent tells me how many copies of the base I have multiplied together. And so this really becomes 2 to the y equals 2 to the 4. Well, the only way for that to work is for y to equal 4. Let's see if we can do another one of those, see if we can make that make a little more sense. All right, so instead of y equals log 216, let's do y equals log 5 of 125. Well, if I use the same idea, log base a of x equals y, this is the pattern I'm trying to follow. This would be log base a of x equals my y. That would mean that my a was 5. Well, and that I've got my a to the y equals x. These two are the same. Okay, well then I'll have a is 5 to the unknown value equals x, which is 125. Well, now let's think about what is my 125. 125, the last digit's divisible by 5, so the whole thing's divisible by 5. And if I think about it, 5 times 25, well, 4 times 25 would be 100. So 5 times 25 is 125. And so I've got 25 and 5 there. Another way to do that, since I'm letting you use a calculator, is to take 125 and divide it by 5, and that would let you know what you'd have to multiply by 5 to give me 125. And so that's another way to leverage the technology to find the answer. Okay, and 25, well, that's 5 squared, right? So I've got 5 times 5. Well, that's 3 5s multiplied together. That's the same thing as 5 cubed. And so what I have is I have 5 to the y equals 5 cubed. And the only way for that to work is for y to equal 3. Okay. Let's take a look at one that might not be as obvious. Let's take a look at natural log of 1. And it's assumed y equals natural log of 1. Well, what did we say? We said that the log base a of x equals y is the same as a to the y equals x, right? Let's get ourselves a new page here. Natural log ln, that's one of those special logs, right? There were 2 special logs. ln, let's use a different color. ln was log base, well, I should say ln of x. ln of x is the same thing as log base e of x. It's the natural log. E is very common in population growth, which would be one of the reasons that we call it the natural log. And then log without any base written is the other of the two that you actually see on your calculator, right? Because I got log, and then I've got natural log. Those are both on my calculator. All right, and so I got log, and that's actually log base 10 of x. And so our names for these two is that is my natural log, and that is my common log. Okay, well, so what I really have here is I have my natural log of 1. I'm trying to evaluate natural log of 1. Well, and so that really, I'm saying y equals log base e of 1. And so that would become e to the what equals 1. Well, remember, e is a number. And so e is not only a number, but it's approximately 2.71, right? Remember, if I hit second and then e, I can find out what that value is. Oh, 2.72. I forget rounding. Rounding is important. Approximately 2.72. Okay, so how do I use an exponent to turn a constant value into 1? Well, there's really only one way to do it, and that's to use something to the 0, right? Because any power raised to the 0 is 1. The best way that I've heard it described is that something to the 0 is the same thing as a to the 1 minus 1, which is the same thing as a to the 1 times a to the negative 1, which is the same thing as a divided by itself, which equals 1. So if that helps you remember, great. If not, that's just the best explanation I've heard for why a to the 0 equals 1, any number other than 0. This is a not equal 0 because I can't divide by 0 there, right? Okay, well, what that literally means is that the only way for this to work is for this to be e to the y equals e to the 0 equals 1, y equals 0. And if I go back to what I know about exponential graphs, that also makes a lot of sense because this is an exponential with a base that's greater than 1, and the y-intercept of that is always going to be at x equals 0. And so that makes sense that my variable would have to equal 0 in that case. Okay. Yeah, I think that's a good set of examples for this type of simple problem.